お、すごいね。Okay, hello everyone. Welcome to this session. This is a session 1B. The session theme is digital fabrication and construction. My name is Tomohiro Fukuda from Osaka University, Japan. I'm a session chair of this session. So, yes. Okay. Okay, we have a 45 minutes session. So this is the agenda of this session. At first, introduction from me, and as you may know, you watch the video and read the proceedings, but every presenter has present very brief key points. We invite 12 research in this session. And then the question and answer session from me or the other presenters or from audience. So, okay, next. Okay, for audience, please use the Q&A box if you have questions. And we have 12 researches. And if you have questions to all the presentations, please feel free to ask questions. But if you have some presenters to ask directly, so if you input the questions, please include the presenter's name so that we know who the question is for. Okay, please contribute. So today, in this session, we have 12 researches. This is the first 6 presenters. Kathleen, Shihan, and Sheriff. Sheriff will be absent, and Shiyu and Matthias. And next 6 presenter is Thomas and Alexander, Alfista, and Stella and Roberto, and Giulio, and August. So from now, let's start. Let's begin the brief key points of each presenters, from each presenters in 90 seconds, or the max is 2 minutes, please. Okay, at first, I invite Kathleen. Kathleen, can you hear me?
Yeah, can you hear me?
Yeah, okay, please introductions. And please let me know to the next slide.
Cool. Hi, I'm Caitlin. I'm from Victoria University of Wellington, and I finished my master's. My master's was on the topic of how can an alternative recycling system be created for waste plastic to create a circular economy using additive manufacturing. And my supervisor was Kevin Sweet and Jill Bing. Could you please go to the next slide? My thesis started by doing research into waste plastic, and from here I collected a lot of waste plastic. Then this waste plastic was then shredded and dried. Then the plastic had to be shredded so it could be used on the spool machine. And then from here I introduced the circular economy, looking at how currently this linear approach to waste, we could turn it into a circular model. So I looked at how additive manufacturing could be used to do this and turning the waste plastic into filament to 3D print with. So I came up with a wall system that could be used to test the filament and see how it performed. A parametric system was developed using Grasshopper and a sine wave equation to create the design. The tiles were then divided up into printable sizes and a toolpath was created. A range of parameters were tested to try to figure out the limitations of the material, and a performance criteria was created to reflect upon each design and see how I could develop it to get a final wall tile. Unfortunately, I couldn't print a full-scale wall as the workshop closed. You can see in the end image there is an example of how the wall tiles would look. Yeah, I'm not sure if you can see my mouse or not. But it's a clipping system, so no fixtures are needed. As you can see in the middle images there, it clips onto each other, so then they can be taken off and either reused or recycled at the end of their life cycle. So this process created a workflow where the plastic is taken, it is shredded, turned into filament, and then a design is created. Then they are printed and used, and at the end of their life cycle, they can either be reused, biodegraded, or shredded up and used again and made into filament. So thank you.
Okay, thank you very much, Kathleen. Okay, next presenter is Shihan.
Yeah. Hi everyone, this is Han from Singapore University of Technology and Design. We present the result from a workshop, and the fabrication process was done by the student. We print clay as a formwork for concrete casting, and in this paper we address the question that when we do the green wall system in construction, it's always been like a attached layer of a frame or devices on top of the facade or the existing structure, whether there is a way to integrate the functional green wall system into the concrete structure itself. So in this scenario, we don't only print out the formwork, the envelope for concrete casting, we also allocate this kind of lattice structure inside concrete so that the root can be rooted in the concrete itself. So in this scenario, like we print out clay mold and casting concrete and plant on several species of the gum to see how it works. Yeah, this is that idea.
Okay, thank you very much.
Yeah, yes.
I invite Shihan again for the next paper. Please introduce again.
Yeah. For this paper, we kind of target on a very detailed question that we noticed the effect that when we print out the clay through the extrusion, the filament width can be equivalent to the nozzle diameter. While we maintain the extrusion speed and slow down the nozzle movement speed, the filament actually could be wider, which means, let's say if we use a 4mm nozzle, we can produce the 8mm filament width. So in this scenario, how does this 8mm filament compare with the 8mm filament produced by 8mm nozzle? This is the question. In terms of the appearance as well as the mechanical performance, so we did a series of research on that and presented the result in this paper. That's it. Thank you.
Okay, thank you very much. So we got the next. And I got the email, and unfortunately, Sheriff cannot join the sessions due to some issues. So if you come back, if he come back, we invite again, and we can just share his graphical abstract like this. So we shift to fifth presenter, Xiu Feng.
Hello everyone. This paper describes the design and the fabrication process of an adaptive joint using 3D printed mono-material bistable mechanisms. The proposed joint deforms when external forces are applied, achieving two stable states. 3D printing experiments is conducted to explore the possibility of various forms of the joint, which realize bistable by a single material. The experiment primarily solved two problems, namely the selection of materials and how to make the rigid 3D printed material acquires properties of flexibility and softness. Finally, practical applications are shown to prove the future of the joint. And that's all.
Mhm. Thank you very much. Okay, we shift to the next. Matthias.
I'm actually Joanna Taseva, and I'm from ETH Zurich.
And I'm Nick of Tejarolivo. We are two presenters, and we are happy to present a large-scale 3D printing functionally graded facade on behalf also of co-authors Hunjul Kwon, Matthias Leszok, and Professor Benjamin Dillenburger.
This was our thesis project from the Master of Advanced Studies in Architecture and Digital Fabrication at ETH Zurich, a one-year master program organized by the National Center for Competence in Research and jointly taught by the chairs of Digital Building Technologies and Grammatiocolor Research. And if you can go to the next slide, please.
Okay.
The goal of this research was to fully utilize the freedom offered by 3D printing as a fabrication method to design a coherent facade system with embedded multifunctionalities. The three main topics in which we focused on were gradient infill structures, which vary the opacity and translucency of this facade based on their internal size. Second, a non-orthogonal discretization procedure, which subdivided this large-scale facade demonstrator into 8 easy-to-handle panels. And our last focus was an incorporated snapping connection system, which made the assembly and disassembly of these 8 panels quite quick and easy. And that's our quick summary. Thank you.
Okay, thank you very much. So we shift the next seventh presenter, Thomas.
Well, hello everyone, I'm Thomas. I'm architect from the Faculty of Architecture and Design, the Catholic University in Chile, in Santiago. This research explores the fabrication or studies the process of 3D printing by dimensional layers over pretension fabrics in order to generate three-dimensional shapes. So after the tension is released, of the fabric is released, the 3D printed pattern generates a tension and compression over the textile. So for this, we design a mechanical simulator based on the flexible column properties, mechanical properties. So we incorporate all the mechanical principles of the flexible columns in order to predict the final outcome. After, so during this process, the goal was to produce or fabricate with the less amount of energy embedded in materials in order to produce or maximize the three-dimensional final outcome. So during this process, we applied, as I said before, the mechanical principles of the flexible columns, and we combine them and we simulate them using parametric and generative tools. And then we generate an input final shape, a simulated final shape, and then we 3D print it. And then we compare both, and we analyze, and we make the mechanical analysis, and we achieve almost a 98% of precision in between the simulation and the pretensional fabric final physical outcome. So the digital simulator was very close or similar to the final shapes. So during this process, we also explored what if we could 3D print or let's say trick the mechanical principle in order to do straight or 90 degrees angles. And we developed some stingens using machine learning algorithms we developed some stinges in the 3D printer pattern in order to make these final breaks that you can see at the end. That's it.
Okay, thank you very much. So we invite next presenter, Alexander.
Good morning, everyone. I'm Alexander Gert. I'm an industrial designer. And the research is, I'm from the Technion, the East Technology, and I'm planning this. 3D print. Bed now.
Oh.
And our research was to define the way to print in a 90-degree direction without the need of support. If you can play the video in the left side down, yes. And in this way, we can print structures without the printing support. And doing this research, we defined new shape of the cross section of the layers. And when we're moving to the side, we can see in the middle of the presentation the structure of the cross section of the layers. It's not layers, but it's contours that going in 90 degree. And in this way, if you can go to the next slide. Yes, and in this way we defined a few ways that we can use the structures. So we can use the structures as a part of the design, as we can see in downstairs. And in some cases, we can also use those structures to reinforce the structures when we 3D printing large-scale structures as buildings or products that need to be reinforced, like we use in the industrial design called ribs. And also in this way, we can print 2 layers with closed structures without with a void between them, as you can see downstairs at the H-beam. And so we hope this additional method can be used in also small scale, but also in the large scale manufacturing, and be another additional method to print with, like support structure or freeforming. That's all.
Okay, thank you very much. Okay, we go to the next. Abhipsa.
Can you hear me?
Yes.
Okay. So this project was my master's project from Singapore University of Technology and Design. Our research was about the design and fabrication of a modular system composed of prefabricated concrete struts that are cast within knit tubes and assembled together with 3D printed joints. So you can see on the left, we went through the process of figuring out varying basic parameters like yarn material, for example, to find out what combination worked. And then we went through the iteration of geometry to find out which geometry worked best for the result we wanted. So this all resulted in a kit of parts for the formation of shell-like geometries, like you can see on the right. Yeah, that's all from me.
Okay, thank you very much. Very comprehensive and quick. Okay, thank you. The next, Kenny Tracy.
Me, Stella.
Oh yeah, Stella. I'm sorry. Yes, Stella. Yeah.
So, hi, my name is Stella Liu. I'm from the Singapore University of Technology and Design. This research comes from my master's thesis. It is about incorporating water-actuated chitosan films with architectural structures to create passively responsive architecture of the future. So chitosan is made from chitin. It's found commonly in the exoskeleton of crustaceans and insects. It is hygroscopic, meaning it expands and contracts with the absorption of moisture. So the Kathleen biopolymer films that we used in this research was invented by Javier Fernandez and his team at the Fermat lab. So with his collaboration, we were able to make these films ourselves in his lab. And applying these films, we specially designed 3D printed compliant mechanisms to achieve a self-actuating system. So if we click on this video down here, you'll be able to see. So this video showcases a prototype singular hydro-compliant panel responding to wetting and then drying of the Kathleen film laid over it. So the research presents later the design process and fabrication of the compliant mechanisms used, and that of the panel itself, the results of the prototype and the experiment, and a simple possible application of it architecturally in the future. Yeah, so this
secondary prototyping experiment for a 6-axis connection node. After an assembly test for the prototype node, in order to assess the production accuracy, we 3D scanned it and found how the maximum deviation, the value is 6.7 millimeters, is located in the top areas. Furthermore, the 88.5% of the scanned points are included in the deviation range of ±1 millimeters. In order to investigate the internal organization of the steel fibers, we cut one of the prototyped nodes, and we found how most of the fibers are accumulated at the bottom areas of the geometry in respect to the orientation adopted during the concrete curing. Thanks for your attention.
Okay, thank you. Okay, we invite the last presenter, Ozguk. You're here? Is here? No here? No here. Okay, no here. Okay. Okay, just sharing the brief abstract and by Ozguk. Okay, CAM as a tool for creative expressions, informing digital fabrication through human interactions. Okay, if he or she come, I will invite again. Okay, so thank you for your brief presentation of your key points of research. So next we turn to the question and answer sessions. So for audience, if you have a question or the comments, please input Q&A box. Okay, I pick up some of them and ask the presenters. If you have a similar question to some only the one presenter or a few presenters to write down the name to ask a question. Okay, so during the considering the questions from the audience, I prepare 3 questions. So the first one is okay. I finish the sharing the screen and okay, stop share. Okay, and okay, we are more meeting type. So my first question is, what were most difficulties of your research to achieve your conclusions? I write down also in the question and answer box, like okay, oh, I cannot I cannot input. Okay, then my question in the chat box. So this time you can published research fruit through some difficulties and achieve your research fruits and the publications. So I would like to know for the audience, for me and the other presenters, what were the most difficulties of your research in this research to achieve your conclusions. So please show your process and your ideas to share for us. So if you prepare some more answer, raise your hand, or otherwise I ask to you by the line. Kathleen, do you have some ideas?
Yes. So the thing for mine was sourcing the plastic because it had to be of a good quality, and then also the whole process was quite time consuming because I had to collect it and then shred the plastic, and then I had to dry it in an oven, and then also making the filament. And the machine I used to make the filament, it was quite hard to get a consistent diameter of the filament. So this affected the overall print.
Okay, thank you. Okay, Shihan, you can distinguish the two papers.
Yeah, cool. All right. For the first one, the green wall fabrication, the major problem we are meeting actually is we are using clay to take place of soil. But the problem is clay is not a good kind of like ground type of material for plants to grow because it's too dense and air can't go in, and there's only a few of the special type of plants can grow in clay. So in that scenario, like in order to match the fabrication property, since some of the soil is very difficult to control the sand ratio as well as the other kind of like maybe small stones inside it. So the fabrication process might be very difficult. In that scenario, like the material property is the main challenge here. So in short, that we take clay, advantage of clay that is easy to print, but bad for the plants to grow. Yeah, so that's
Okay.
the main
How about
challenge
next?
of the, yeah. The next is actually to use a small nozzle to produce a wider filament is not that easy. It requires a lot of kind of process control and calibration about the extrusion speed, as well as the robotic arm movement speed, and also to how to keep all the specimen to maintain them in the rest status, means the water ratio, how to pack them and storage, as well as the long time kind of like testing precise, all these type of things. For the rest, I guess is quite easy. And also the data kind of analyzation took an extremely long time. Yeah, since there are quite many years of data. Yeah.
Okay, thank you very much. So, okay, Yufan, please, do you have an answer?
The most difficult part of my research is how to make the rigid 3D printed material acquires a property of flexibility and softness. And I didn't have the ability to make the accurate mathematical calculation. So it depends on the many experiments to solve the problem. That's all.
Okay. So you developed the software by yourself, or some customized?
It's just to make the material more thin, and so it's soft.
I see. Thank you, Matthias, and your colleagues.
So regarding our 3D printed facade, I would say one of the main issues that we found during the development of designing the facade was the scaling up of the facade itself. We started with some small scale and middle scale experiments, And for example, for the connections, once you scale up the 3D printing process, you find out that basically the tolerances you defined in the very beginning, don't match anymore. So you have to, again, like try to fine tune the new tolerances so they work with a low resolution 3D printing, so as to say.
Okay, thank you. Andrew, you have also? No? It's okay?
Can you hear?
Also,
Okay. Okay, thank you. Thomas? Thomas?
Yes. Well, I think that it was the analysis of the column deflection because it's mainly based on how finite linear elements, like the density of the dimension, is influenced by restrictive forces of the textile. So in order to parameterize that, to making the simulations was a very complex factor because we were finding some critical aspects in the deflection column, on the deflection mechanical column principle, in order to decrease the, let's say, the layering of the 3D printing, because our main objective was to 3D print less in order to maximize the final form. So there we spend most of the time trying to program the simulator in a proper way in order to have a, let's say, a very close definition of what we were achieving in the physical models. So yeah, that's and in that part we experiment with at least 5 or 6 different mathematical equations, introducing into the parametric software. Yeah, that's it.
Okay, thank you. Alexander, please.
I think because it's a little bit new method and there is no many mathematical equations about the cross section and how the form of the material will be fused to each other, then we focused on the distance between two roads to check what kind of fusion and what appearance it will take, but the gravity and the material temperature and the material shrinkage and etc. was too many parameters that was involved, and it was very hard to understand which of the time, then the structure is shrinkage inside and all the structure is full, and it's not our parameters and we cannot include it, but it was very challenging.
Okay, thank you. Oh, sometimes the connectivity is not so good, but yeah, we can listen to your answer. Thank you. And yeah, Abhispa.
Yeah, during our process, one of the early and major challenges was getting the yarn material right, as that affects the geometry of a tube. So coming to the conclusion that the tube should be mostly elastic was a big breakthrough, because we want to mitigate hydrostatic pressure as much as possible, to not have any deflections in the tube. So that was one of our challenges, and once we figured that out, the process got a lot smoother. Yep.
Okay, thank you. Stella, please.
The most difficult thing for me was our research was a lot into the design of special compliant mechanisms that would work in terms of control of flexibility for this hydroscopic panel. So from the calculations, it was really hard to achieve something accurate. So majority of it was based on fabrication testing. So we did multiple different types of 3D printing materials to test flexibilities. and also the bounciness of the 3D material to return to its original form after multiple states of actuation. Yeah. So.
Thank you. Okay, Robert?
Okay,
No.
I'm
Giulio.
Yeah,
Sorry,
yeah.
Giulio. Yeah.
Yeah, during this research, many conceptual and practical challenges were addressed. In addition to the aspect concerning the definition of an integrated design to fabrication workflow, the selection of the actual compound proportions, as well as the identification of the printing setup, were fundamental elements for a proof of concept that opens perspective for a new type of reversible concrete construction. Thanks.
Okay, thank you. Okay, we have less than 10 minutes, and we got one questions from the Candy. Can you look at the Candy's questions? Open to the question in the box. So Candy says, many of the presentations focus on details, material-oriented technological questions. So how do you see them feedback into architectural design? So raise your hand if you prepare, and also please, very brief answer is welcome. Okay, Matthias, let's walk. Etihad team. Yes.
I would say that in some cases, depending on which material was used, like concrete, for example, you could go directly into applying it to architecture. But in our case, we used PLA as printing material, which is not very durable. So when we continue doing this research, we would have to look into other materials that would be weather resistant, or last a lot longer than PLA would, something that would have UV resistance, or potentially glass, although that's very much still in the beginning stages of printing with it. So
Yeah. Okay, Shihan.
Yeah, because I guess for a lot of us, the reason we are doing this kind of digital fabrication research is there's no such a technique in the market for the architectural application. So in this scenario, we have to try it out by ourselves. And after finishing the prototyping stage and prove the concept, how to advance the research. We expected there are some kind of like mechanical engineer engaged to help us to detail all the configurations and material properties, but most likely they're not. So we have to do it by ourselves to make it a real applicable kind of like a technique in architectural field. That's it.
Mm-hmm. Any other answers? Raise your hand. Oh, Tracy, Kate Kennis.
Yeah. Yeah, for Stella's project, our project, we have some other projects with a larger scale trusses. I think the problem is that the film is edible. So microbes and other animals can eat it. So that's kind of a problem. So I think there's some challenges to that, but the configuration for the compliant mechanism that Stella worked on so much is quite applicable if the materials could be, say, injection molded and maybe fiber reinforced. So there's examples of building products that are like this. So this different types of manufacturing might make things sort of scalable.
Thank you. Alexander, please. Alexander, do you have?
Yes, and I will try to answer both questions. I will turn off the video because of the connection. And I think the research is in this research it's in medium and small scales, but using thermoplastic materials, we can see also in the NASA project as Marsha that they're building very large scale structures on the field, and those materials will act in the same way that we printed with the ABS material, because they can fuse and solidified with by cooling the material. And I will try to read the question. If I understand right, that the second question and the feed, the horizontal shape, they falling down in the large. Sometimes it's not all the times. The shape of the plate it fall down, and because it's not solidified enough, or it also can be added more material because we are shape larger materials and larger shapes closing all the shape with the horizontal forming, then it can be solved. But yes, in large horizontal forms, it is more problematic for now to shape those structures. But it also can be solved by 2 layers or 3 layers of forming, and then it will be straightforward. I hope that I answered the question right. Understand it.
Okay. Thank you. Oh, you answered to Yasushi also.
Yeah.
Okay, thank you. Okay, any other answers to Candy's questions? How about Julio?
Yeah, this is interesting because, yeah, I agree with that. Our research is just one step through reaching a consistent applicability of FDM formwork for circular concrete construction. We need to focus more in future on the application of this approach in real scale to understand better both the structural behaviors of these tiny elements and the detailing aspects for the connections. What we have in mind is using this workflow for an on-site production used for temporary settlements.
Okay, thank you. Yeah. Okay, we are approaching to 12 o'clock. So if you have some more comments to answer to Candy, or some comments briefly, please raise your hand. Thomas, do you have something? Do you have something to say? Yeah, please.
Yeah, maybe just to say that the change of scale is not linear, it's always exponential. So it's very hard in order to do like small scale prototypes in order to rescale them. So particularly in my case, apart from mechanical constraints of 3D printing that you can use robot arm and so forth, then you have this problem of scale of gravity and other mechanical principles that might affect in this process. So I see, if I see closer to architectural scale, maybe will be architectural elements for facades and so forth, but not at such a big scale that I insist this change of scale should be much more exponential and new research to the build in order to build it.
Okay, thank you very much. Okay, time is coming, so we should finish, and yes, it should be punctual. And anyway, okay, I have to say closing. Thank you for anyway attending the conference due to time differences from Europe and US, or also Asia is also have a time differences, and through the lunchtime break, and we have a very exciting time and reading the book, the papers, and watching the videos also. So after these sessions, if you have an answer to Candy or the Yasushi more, please write down the text or the email to them directly, and continue to discuss and keep in touch is very important to emphasize and improve your research, I think. Okay, thank you very much. Have a nice day. Yeah.
Thank you.